Good evening and welcome to Dreamy Academy. Tonight we embark on a quiet journey into the very fabric of existence, exploring the profound and intricate world of organic chemistry. As we begin, I'd love to know where you're watching from, your city, your country, perhaps even what the night sky looks like outside your window. If you enjoy these peaceful explorations of science, please take a moment to like the video and subscribe. It truly helps this little corner of quiet curiosity grow. To those already subscribed, thank you sincerely for being part of this slow and thoughtful adventure. Right now, as you listen, forces older than mountains are shaping the atoms in your bones, in the air you breathe, in the very device that carries my voice to you. Every breath you take contains atoms that once flowed through dinosaur lungs, through ancient oceans, through the hearts of stars long dead. This isn't just poetry, it's the quiet, undeniable truth of the universe. We are made of stardust, yes, but more intimately, we are made of patterns, of arrangements, of specific dances performed by those fundamental particles. Consider the simple act of existing. Your body, a symphony of billions of chemical reactions occurring every second, a complex, self-sustaining system built from a handful of fundamental ingredients. The universe, in its vastness, has found a way to arrange matter into forms that can think, feel, and wonder about their own origins. And at the heart of this wonder, this intricate dance of life and matter, lies a single element, unassuming yet utterly extraordinary: carbon. Organic chemistry is not just a branch of science. It is the language of life itself. It is the story of how simple atoms, guided by elegant rules, can weave themselves into molecules of breathtaking complexity and function. It's the silent architecture behind every leaf, every thought, every taste, every scent. It's the reason fire burns, why sugar is sweet, why your DNA carries the blueprint of who you are. To understand organic chemistry is to begin to read the universe's most beautiful and intricate poem, whispered across billions of years. It asks us to slow down, to look closely at the invisible, to appreciate the profound elegance hidden within the ordinary. And as we drift through its landscapes tonight, I hope you find not just knowledge, but a deep, lulling sense of connection to the wonder that surrounds and defines us. Have you ever noticed the sheer stuff of the world around you? The smooth coolness of a ceramic mug, the crisp rustle of a leaf, the warm glow of a wooden table, the soft fabric against your skin. Each is profoundly different, yet all are built from the same fundamental ingredients, the same quiet architects of matter. Tonight, we begin our journey by contemplating these builders, these tiny, intricate structures that give rise to everything we see, touch, and feel. Let's begin by considering the most basic unit of all matter: the atom. Imagine, if you will, shrinking down, past the visible world, past dust motes dancing in a sunbeam, past the intricate veins of a leaf, until you reach a scale almost beyond human comprehension. Here you would find not solid spheres, but shimmering clouds of probability, tiny universes of energy and force. An atom is less like a miniature billiard ball and more like a whisper of existence, a quantum poem. At its heart lies a dense, positively charged nucleus, a tight cluster of protons and neutrons. And around this nucleus, not orbiting like planets, but existing in fuzzy energetic clouds, are electrons. These electrons are the true artists of chemistry, the ones that dictate how atoms interact, how they connect, how they build the world. The atom is mostly empty space, an astonishing thought when you consider the apparent solidity of a stone. If the nucleus were a pea in the center of a football stadium, the electrons would be tiny, buzzing motes of energy somewhere within the stadium's vast, empty expanse. These atomic architects come in many varieties, each defined by the number of protons in its nucleus. We call these varieties elements. The periodic table, that grand library of elements, is not just a chart, it's a map of creation, listing every fundamental building block the universe has cooked up. From hydrogen, the simplest and most abundant, to the heavier, more complex elements forged in the hearts of dying stars, each has its own unique character, its own way of interacting. And among these elements, one stands out with an almost magical versatility, a quiet brilliance that underpins all life, and an astonishing array of non-living things: carbon. To understand carbon's magic, we must first understand the concept of a chemical bond. Atoms, in their natural state, are often restless. They seek a kind of stability, a completeness in their electron clouds, much like a tiny, energetic dancer seeking a partner to complete a graceful turn. The most common way for atoms to achieve this stability is by sharing electrons. This act of sharing is called a covalent bond, a delicate but powerful embrace where two atoms mutually gain a sense of completeness. Imagine two dancers, each needing an arm to complete a pose. Instead of taking an arm from somewhere else, they simply link arms, satisfying both needs simultaneously. This shared electron pair becomes a strong, invisible glue holding the atoms together, forming a molecule. Now, consider carbon. Carbon is an exceptional dancer. It has 4 electrons in its outermost shell, and it ideally wants 8 to achieve stability. This means carbon can form 4 covalent bonds reaching out in 4 different directions, like a spider with 4 strong silk threads. Most other elements are more limited. Hydrogen forms 1 bond, oxygen typically forms 2, nitrogen usually forms 3, but carbon, with its 4 arms, is the ultimate molecular builder, the master architect of the microscopic world. It's like having a Lego brick that can connect on 4 sides, allowing for an almost infinite variety of structures. This ability to form 4 stable covalent bonds isn't just a number, it's the secret to carbon's extraordinary versatility. Imagine a single carbon atom. It can bond to 4 hydrogen atoms, creating the simplest organic molecule, methane, the gas that fuels your stove or bubbles up from swamps. But it doesn't stop there. Carbon atoms can bond to other carbon atoms, and then those carbon atoms can bond to yet more carbon atoms, stretching out into long, elegant chains. They can form branching structures like tiny molecular trees. They can even curl back on themselves, forming stable rings. This capacity for self-linking, for creating extensive skeletons, is what truly sets carbon apart. It's the foundation of an entire universe of molecules. Picture these carbon skeletons, a long, winding chain of 20 carbon atoms, each connected to 2 others, with hydrogen atoms filling in the remaining bonds, creating a waxy, greasy substance. Or a 6-carbon ring, flat and strong, like a tiny molecular hexagon, forming the core of many aromatic compounds, responsible for the scents of cinnamon or vanilla. These are the hydrocarbons, the simplest family of organic molecules, built only from carbon and hydrogen. They are the molecular scaffolding upon which all other organic structures are built. They are the fuels that power our world, from the gasoline in our cars to the fat stored in our bodies. Their diversity is staggering, from the lightest gases to the heaviest tars, all variations on carbon's patient, multi-armed embrace. The wonder here lies in the sheer combinatorial power. With just 2 elements, carbon and hydrogen, and carbon's unique ability to link endlessly in varied geometries, the number of possible molecules becomes astronomical. Each slight variation in the chain's length, each subtle difference in branching or ring formation, creates a molecule with distinct properties. One might be a gas, another a liquid, another a solid. One might be inert, another highly reactive. This is the quiet genius of carbon. It provides the structural backbone, the endless possibilities for arrangement that allows for the incredible diversity of matter we observe. It's like having an alphabet of only 2 letters, but with rules so flexible that you can write every story ever told. This intricate architecture, built atom by atom, bond by bond, is not just a scientific curiosity, it is the very foundation of life. The complex molecules that make up your cells, your DNA, your proteins, your fats, your sugars, all have carbon skeletons at their heart. Life, in essence, is carbon-based chemistry that learned to organize itself, to replicate and to evolve. The quiet architects we've explored tonight, particularly the unassuming carbon atom, are the reason for your existence, for the vibrant tapestry of the biosphere, for the complex world of materials we interact with every day. There's a particular comfort in understanding that the profound complexity of life emerges from such elegant, simple rules at the atomic level. So we've seen how carbon, with its 4 patient arms, builds vast, intricate skeletons of chains and rings, forming the foundation of countless molecules, from the simple methane to the complex waxes. But this raises a quieter question. What happens when other elements, with their own unique characters and bonding preferences, join this carbon dance? What happens when oxygen, with its 2 bonds, or nitrogen, with its 3, or the playful hydrogen, with its single bond, enter the scene? How do these additions change the personality of a molecule, giving rise to new functions, new properties, and an even richer tapestry of chemical possibilities? That question leads us into the world of functional groups, where the subtle addition of a few atoms can transform a simple hydrocarbon into something utterly new and vital. Last time, my friends, we peered into the quiet brilliance of carbon, that unassuming yet utterly extraordinary element. We watched it weave intricate molecular tapestries, forming the very scaffolding of life with its unparalleled ability to link, branch, and ring. We understood how these endless carbon chains, these silent architectures, form the foundational skeletons upon which the universe builds its most complex and breathtaking structures. We saw carbon, the master builder, constructing the vast, diverse world of hydrocarbons, from the simplest methane to the sprawling networks within our own cells. But imagine for a moment a magnificent, intricate building, a grand cathedral perhaps, with towering spires and sweeping arches, all crafted from the purest, most resilient stone. This is our carbon skeleton, strong and foundational. Yet what gives such a structure its character, its purpose, its ability to inspire awe or provide comfort? It is not merely the stone, is it? It is the stained glass windows that capture the light in shimmering hues, the carved wooden doors that invite entry, the delicate frescoes that tell ancient stories. It is these additions, these specific embellishments, that transform a mere structure into a place of profound meaning and function. In the realm of organic chemistry, these embellishments are what we call functional groups. If the carbon skeleton is the robust sentence, the fundamental statement, then functional groups are the vibrant verbs, the descriptive adjectives, the crucial punctuation marks that give the sentence its true meaning, its emotional resonance, its very life. They are specific arrangements of atoms, often involving elements like oxygen, nitrogen, sulfur, or phosphorus, which attach themselves to the carbon backbone. And with their arrival, the entire personality of the molecule shifts. its reactivity changes, its interaction with its environment is utterly transformed. Think of it this way. Our quiet architects, the carbon atoms, lay down the blueprint, the very bones of the house. But the electrons, those true artists of chemistry, dance with other elements to add the plumbing, the wiring, the heating, the very soul of the home. These functional groups are the sites of action, the places where chemical reactions happen, where molecules recognize each other, where life's intricate processes unfold. They are the tiny, shimmering flags that signal a molecule's purpose, its desires, its potential. Let us embark on a gentle journey through some of these fundamental functional groups, marveling at the profound changes a few extra atoms can bring. We will approach them with the same quiet wonder, the same contemplative spirit that we brought to the carbon atom itself. Our first stop is a group that often introduces a touch of the familiar, a hint of the wetness of life, the hydroxyl group. It's composed of a single oxygen atom bonded to a single hydrogen atom, and it attaches directly to a carbon atom on our molecular skeleton. We write it as oxygen, as you might recall from our grand library of elements, the periodic table, is one of those elements with a strong pull on electrons. It is more electronegative than carbon or hydrogen. This means that when oxygen forms a covalent bond, it doesn't share the electrons perfectly equally. It gently but persistently tugs them a little closer to itself, creating a slight negative charge on the oxygen and a slight positive charge on the hydrogen and the carbon it's attached to. What does this subtle tugging, this slight imbalance achieve? It creates sorb polarity. Imagine a tiny molecular magnet with a slightly negative end and a slightly positive end. This polarity is crucial. It means that molecules bearing a hydroxyl group, which we call alcohols, are often much more comfortable in water, which is itself a highly polar molecule. They can form hydrogen bonds, those delicate but powerful attractions that allow water to dissolve so many substances. Consider ethanol, the alcohol found in many beverages. Its carbon skeleton is quite small, just 2 carbons. But the presence of that single OH group transforms it from a relatively inert hydrocarbon into a molecule that readily mixes with water, that has a distinct sharp aroma, and that interacts profoundly with biological systems. It's like adding a small shimmering beacon to our carbon structure, announcing its presence to the aqueous world. This single oxygen and hydrogen atom, a tiny addition, fundamentally changes how the molecule behaves, how it tastes, how it smells, how it dances with other molecules. It's the difference between a dry piece of wood and a glistening, dew-kissed leaf. Next, let us turn our attention to the carbonyl group. Here we encounter a double bond, a more intense embrace between atoms. The carbonyl group consists of a carbon atom double bonded to an oxygen atom. This double bond is a powerful feature. That oxygen atom, still quite electronegative, pulls even more strongly on the electrons in the double bond, making the carbon atom to which it's attached quite electron deficient, quite ready to react. The carbonyl group is like a bright, focused spotlight on our molecular stage, drawing attention and directing the flow of electrons. When this carbonyl carbon is bonded to at least one hydrogen atom, we call it an aldehyde. Think of formaldehyde, a simple aldehyde with a pungent, distinctive odour. If the carbonyl carbon is bonded to 2 other carbon atoms, it's a ketone. Acetone, a common solvent often found in nail polish remover, is a familiar ketone. Aldehydes and ketones bring entirely new textures and scents to the molecular world. They are often volatile, easily evaporating to reach our olfactory senses, giving rise to the sharp, sometimes sweet, sometimes fruity aromas we associate with many organic compounds. They are also highly reactive, serving as key intermediates in countless biochemical pathways, participating in the intricate dance of metabolism that sustains life. The double bond to oxygen is not just a stronger grip, it's a declaration of increased activity, a heightened sense of purpose for that particular part of the molecule. Now, let us combine elements of the previous two. What happens when a carbonyl group and a hydroxyl group decide to join forces, to stand together on the same carbon atom? We get the carboxyl group. This is a carbon atom double bonded to one oxygen, the carbonyl part, and single bonded to another oxygen, which in turn is bonded to a hydrogen, the hydroxyl part. This combination is truly remarkable. The combined electron-pulling power of both oxygens on that central carbon atom, and especially on the hydrogen of the hydroxyl, makes that hydrogen exceptionally easy to release as a proton, H+. This, my friends, is the very definition of an acid. Molecules containing a carboxyl group are known as carboxylic acids. Think of the crystang of vinegar, which is dilute acetic acid, or the refreshing sourness of a lemon, rich in citric acid. These molecules, with their humble COH group, have the ability to donate protons, to interact with bases, to profoundly influence the pH of their environment. They are crucial players in everything from food preservation to the complex buffering systems within our blood. The carboxyl group is like a tiny, eloquent speaker on our molecular stage, capable of asserting its influence, changing the very nature of its surroundings with the gentle release of a single proton. It is a testament to how the precise arrangement of atoms, not just their presence, dictates their profound function. As we continue our exploration, let us invite another crucial element to the dance: nitrogen. When a nitrogen atom, along with its associated hydrogen atoms, attaches to a carbon skeleton, we form an amino group, NH2. Nitrogen, like oxygen, is electronegative, but it also possesses a special feature: a lone pair of electrons. These two unshared electrons on the nitrogen atom are like an open, welcoming hand, ready to reach out and accept a proton. This makes molecules with amino groups, which we call amines, bases. They have the capacity to accept protons, to neutralize acids, to act as proton sponges. Amines are fundamental to life. They are the very building blocks of proteins, the endlessly diverse macromolecules that perform almost every function within a living cell. Each amino acid, the monomer of proteins, contains at least one amino group and one carboxyl group, creating a delicate balance of acidity and basicity that is essential for their biological roles. The amino group is like a soft, receptive cushion on our molecular structure, ready to embrace a passing proton to bring balance and stability to its environment. It is a group that signifies interaction, connection, and the very essence of biological structure. We could continue this journey exploring the sulfhydryl group SH that gives garlic its pungent aroma and is vital for protein structure, or the phosphate group SAUSH-PO4 that forms the backbone of DNA and is the energy currency of life itself. Each new functional group introduces a unique set of properties, a different way of interacting with the world, a new chapter in the molecular story. What emerges from this exploration, my friends, is a profound appreciation for the elegance of organic chemistry. The carbon skeleton, so robust and versatile, provides the foundational architecture. But it is the functional groups, these small specific arrangements of other atoms that truly bring the molecules to life. They are the brushes that add colour to the canvas, the notes that form the melody, the words that compose the poem. Each functional group is a distinct chemical personality, a unique set of instructions for how a molecule will behave, how it will react, how it will contribute to the grand, intricate symphony of life. They are the keys that unlock specific biological functions, the signals that allow cells to communicate, the very mechanisms by which energy is harvested and transformed. As you look out into the quiet night, perhaps at the stars shimmering beyond your window, remember that the same fundamental principles we have discussed are at play everywhere. From the simplest sugar molecule to the most complex protein, from the scent of a rose to the intricate dance of photosynthesis. It is the silent architecture of carbon, adorned and animated by these wondrous functional groups, that orchestrates the universe's most beautiful and intricate poem. Next, we will begin to explore how these molecules, built from carbon skeletons and adorned with functional groups, arrange themselves in three-dimensional space, and why this spatial arrangement is not merely an aesthetic detail, but a crucial determinant of their function, their very identity. We will discover that in the molecular world, position is power, and shape is destiny. Welcome back, my dear fellow travellers, to our quiet journey through the dreamy academy. We've spoken of carbon's extraordinary versatility, its silent brilliance as the master architect, forming the very backbone of life. We've explored the vibrant personalities that functional groups lend to molecules, transforming simple structures into a symphony of purpose. Now, as the soft glow of the evening deepens outside your window, inviting contemplation, we arrive at a truth so fundamental, so exquisitely simple, yet so profoundly impactful, it shapes the very fabric of existence. Shape is destiny. Imagine, if you will, a universe where every whisper of life, every intricate biological dance hinges not just on what atoms are present or how they are connected, but on their precise arrangement in the vast shimmering expanse of three-dimensional space. This is the realm we step into today, a world where a subtle twist, a gentle turn can mean the difference between nourishment and poison, between a healing balm and a harmful substance. It is a testament to the universe's exquisite design, a secret language whispered by the molecules themselves. We begin with a concept known as isomerism. The word itself holds a quiet poetry derived from Greek roots meaning equal parts. And that is precisely what isomers are. Molecules that possess the exact same molecular formula, the same number of each type of atom, but are nevertheless distinct, unique entities. It's like having the same set of Lego bricks, but building two entirely different structures. The bricks are identical, but their arrangement, their connectivity, their spatial orientation renders them distinct in every meaningful way. Our first encounter with this quiet marvel brings us to structural isomers, sometimes called constitutional isomers. Here the difference lies in the very connectivity of the atoms. While the atomic count remains identical, the atoms are linked together in a fundamentally different order. Think of it this way. You have 4 carbon atoms and 10 hydrogen atoms. How many ways can you connect them? One way might be a straight unbranching chain forming what we call n-butane. It's a simple linear arrangement like a quiet train of 4 cars. This molecule exists as a gas at room temperature and is a common component of natural gas. But what if we take those same 4 carbons and 10 hydrogens and instead of a straight line, we create a branched structure? One carbon atom might find itself at the center, quietly embracing 3 other carbons, each with its own retinue of hydrogens. This forms isobutane, a molecule with the same formula, C4H10, but a different shape, a different internal architecture. Isobutane, unlike its straight-chain sibling, has a slightly lower boiling point, a subtle difference that speaks volumes about the impact of its branched form. It's still a gas, still flammable, but its physical properties are distinct. These two molecules, though born of the same ingredients, possess different personalities, different boiling points, different densities, because their internal scaffolding, their very constitution, is different. It's a quiet revelation, isn't it? The same ingredients, but a different recipe for assembly, leading to entirely new outcomes. Now let us take a deeper breath, for we are about to journey into the heart of three-dimensional space where the true magic of shape is destiny unfolds. We move beyond simple connectivity to the delicate ballet of atoms in space, a realm where even identical connections can yield profoundly different molecules. This is the world of stereoisomers. Stereoisomers are molecules that have the same molecular formula and the same connectivity of atoms, meaning the atoms are linked in the same sequence, yet they differ in the spatial arrangement of their atoms. Imagine our molecular dancers still linked arm in arm, but now performing different poses, different orientations in space. These subtle differences, imperceptible to the casual glance at a flat drawing, are everything in the intricate machinery of life. The most enchanting and biologically significant type of stereoisomerism is chirality. The word chiral comes from the Greek word for hand, and it offers us the perfect analogy. Look at your own two hands. They are without a doubt mirror images of each other. Your left hand perfectly reflects your right, but try to superimpose them. Try to place your left hand directly over your right, palm to palm, thumb to thumb. You cannot. They are non-superimposable. They are distinct. This, my friends, is the essence of chirality. A molecule is said to be chiral if it is non-superimposable on its mirror image. And what usually gives rise to this fascinating property in organic chemistry? Most often it's a carbon atom bonded to 4 different groups. This special carbon is called a chiral center or a stereocenter. Think of carbon, our master architect, now holding 4 distinct molecular tools in its 4 tetrahedral bonds. If all 4 tools are different, then its mirror image will be like its opposite hand, a perfect reflection yet distinct. These mirror image, non-superimposable stereoisomers are called enantiomers. They are a pair, always existing together in the mirrored relationship. What's truly astonishing about enantiomers is that they possess nearly identical physical and chemical properties. Their melting points, their boiling points, their solubilities, all are typically the same. It's as if they are twin siblings, sharing almost everything. However, there is one crucial physical property where they diverge: their interaction with plane polarized light. Enantiomers will rotate plane polarized light in equal but opposite directions. One might be a dextrorotatory enantiomer turning the light to the right, while its levorotatory sibling turns it to the left. This property, known as optical activity, is how we often distinguish them in the laboratory. But the real wonder, the profound implication of shape is destiny, reveals itself when these enantiomers interact with other chiral molecules, particularly in biological systems. Our bodies, the proteins, enzymes and receptors within us, are themselves chiral. They're built from chiral amino acids, forming intricate 3-dimensional structures with specific binding sites, like molecular locks. When a chiral drug molecule, for instance, enters the body, it's like trying to fit a key into a lock. One enantiomer, because of its specific three-dimensional shape, might fit perfectly into a receptor site, triggering a desired biological response. It's the right key for the right lock. Its mirror image, the other enantiomer, might be like the left hand trying to fit into a right-handed glove. It simply doesn't fit the same way. It might not bind at all, or it might bind to a different receptor, eliciting a different, perhaps even harmful response. Consider the molecule carvone. One enantiomer of carvone, the case S enantiomer, is responsible for the distinct refreshing aroma of spearmint. Its mirror image, the R enantiomer, has the entirely different aroma of caraway seeds. Both are carvone, both have the same atoms, the same connections, but their spatial arrangement dictates a completely different sensory experience. Our olfactory receptors, those tiny molecular sensors in our noses, are themselves chiral, and they can distinguish between these subtle spatial differences. A more poignant example, though one we approach with quiet reverence, is the drug thalidomide. In the mid-20th century, it was prescribed as a sedative and to alleviate morning sickness. One enantiomer of thalidomide was effective in treating nausea. However, its mirror image, the other enantiomer, was found to be a potent teratogen, causing severe birth defects. This tragic lesson underscored with stark clarity the immense importance of understanding and controlling the three-dimensional shape of molecules, especially in pharmacology. It's a powerful reminder that in the molecular world, a subtle twist of fate, a delicate spatial difference, can hold the balance of life and well-being. Beyond mirror images, there are other types of stereoisomers. Not all stereoisomers are enantiomers. Those stereoisomers that are not mirror images of each other are called diastereomers. Imagine two different non-superimposable molecules that both have the same formula and connectivity, but are not reflections of one another. Perhaps one has multiple chiral centers, and only some of them are inverted in the other molecule, or perhaps they have different arrangements around a double bond. Diastereomers, unlike enantiomers, usually have different physical and chemical properties. This difference makes them much easier to separate in the laboratory, a practical consideration that chemists often leverage. And then, there's another subtle layer to this dance of molecular shapes. Conformational isomers, or conformers. Imagine a single molecule, like ethane, with its two carbon atoms linked by a single bond. That single bond isn't rigid, it allows for rotation. As the molecule rotates around this bond, it passes through various temporary shapes or conformations. Sometimes the hydrogen atoms on one carbon are directly aligned with those on the other carbon, eclipse conformation, which is less stable. Other times they are staggered, creating more space and stability. These aren't true isomers in the same way as structural or stereoisomers, because they can interconvert simply by bond rotation without breaking any bonds. They are simply different snapshots of the same molecule as it twists and turns in space, exploring its most comfortable configurations. It's like a dancer moving through different poses, all part of the same routine, the same identity. So you see, the idea that shape is destiny is not merely a poetic phrase, it is a fundamental principle governing the universe at its most intimate level. From the subtle differences in boiling points of simple alkanes, to the distinct aromas that tantalize our senses, to the life-altering effects of pharmaceuticals, the three-dimensional arrangement of atoms is paramount. It is the silent architecture that dictates function, the hidden language that defines interaction, the delicate choreography that orchestrates the symphony of life itself. As we conclude this chapter, reflect on the quiet wonder of it all. Every living cell, every chemical reaction, every taste, every smell, every healing process, is a testament to the precise, exquisite shapes of molecules. These tiny, invisible architects are constantly interacting, recognizing each other by the unique forms, like perfectly cut puzzle pieces fitting together. Understanding this three-dimensional world is not just about memorizing facts. It is about glimpsing the profound elegance and intricate wisdom woven into the very fabric of existence. In our next gathering, we'll begin to explore how these molecules come together, how they react and transform, constantly seeking stability in new forms. We will witness the dynamic dance of chemical reactions, the very engine of change and creation, always remembering that even in these transformations, shape, always shape, plays the defining role. Until then, let the quiet magic of molecular forms inspire your dreams. In our quiet journey through the molecular landscape, we have contemplated the silent architects, the atoms themselves, and marveled at carbon's singular ability to weave intricate skeletal forms. We've discovered how the addition of functional groups breathes distinct personalities into these structures, transforming a simple hydrocarbon into an alcohol, an aldehyde, or an acid, each with its own unique song and purpose. And then we delved into the profound truth that shape is destiny, revealing how the precise three-dimensional arrangement of atoms, even with an identical formula, can dictate a molecule's entire existence, its interactions, its very essence. But molecules, dear friends, are not static sculptures frozen in time. They are vibrant, living entities in a constant state of flux, ever ready to transform, to rearrange, to dance. If their structure is their identity, then their reactions are their story, their unfolding narrative in the grand tapestry of the universe. Tonight, we turn our gaze to this most dynamic aspect of organic chemistry, the elegant, ceaseless ballet of molecular transformation. We explore how these tiny, intricate structures engage with one another, breaking old bonds and forging new ones, always seeking a whisper of greater stability, a moment of profound equilibrium. Imagine, if you will, the atoms within a molecule as dancers, holding hands, linked in a delicate but powerful embrace. A chemical reaction is simply a change in their choreography. The music shifts, the lights dim, and suddenly those linked hands loosen. Some dancers step away, while new partners emerge from the shadows, ready to join the circle, to intertwine in novel formations. This is the essence of every organic reaction, the breaking of existing covalent bonds and the formation of new ones. It is a testament to the restless energy that permeates all matter, the quiet yearning for a more harmonious arrangement. Why do these transformations occur? What drives this molecular ballet? At its heart, it is often a quest for stability. Just as a rolling stone seeks to settle at the lowest point, molecules tend to move towards lower energy states, where their electrons are more comfortably situated. The universe, in its infinite wisdom, favours order born from a specific kind of energetic tranquility, and the true artists orchestrating this entire process, as we've learned, are the electrons. Their ceaseless movement, their push and pull, their willingness to be shared or surrendered, dictates the very possibility and direction of every reaction. For a reaction to happen, there must first be an encounter. Molecules must collide, not just randomly, but with sufficient energy to overcome the initial resistance, the activation energy. And with the correct orientation, like two puzzle pieces aligning perfectly before they can snap together. Think of it as two dancers needing to meet in the center of the floor, not just bumping shoulders, but gracefully extending their hands, poised for the next step. Let us explore some of the fundamental dances, the archetypal transformations that define the world of organic reactions. Consider first the substitution reaction. This is perhaps the most straightforward exchange, a simple swapping of partners. In this dance, one atom or group of atoms within a molecule is replaced by another. Imagine our molecular dancers, a carbon atom holding hands with four others. In a substitution, one of those partners might gracefully step aside, and another, perhaps drawn by a stronger energetic pull, takes its place. The core carbon skeleton remains largely intact, only a small piece of its identity changes. A classic example involves the quiet alkanes, those saturated hydrocarbons we first encountered, so stable in their single-bonded embrace. They are generally quite unreactive, content in their saturated state. But introduce them to a halogen, like chlorine gas, under the gentle persuasion of light, and a substitution can occur. A hydrogen atom, one of carbon's steadfast companions, might be replaced by a chlorine atom. It's a subtle change, yet it profoundly alters the molecule's personality, its polarity, its potential for further interaction. The molecule, once purely nonpolar, now carries a slight charge imbalance, a new whisper of reactivity. Then there is the lively addition reaction, a dance of expansion, often seen where there's a double or triple bond. Remember those unsaturated molecules, the alkenes and alkynes, with their extra electron density in the pi bonds? These regions are like open arms eager to embrace new partners. In an addition reaction, the double or triple bond breaks, making room for new atoms to attach themselves directly to the carbon skeleton. It's as if two dancers, who were once holding hands and twirling together, suddenly release their grip and each takes a new partner, expanding the circle. The molecule becomes more saturated, its carbon backbone gaining more single bonds. Picture an alkene with its carbon-carbon double bond, a region of quiet tension and potential. Now imagine introducing hydrogen gas in the presence of a catalyst, perhaps a sprinkle of platinum or palladium, those silent facilitators of change. The double bond, that energetic embrace, loosens. Each carbon atom that was part of the double bond now reaches out to embrace a hydrogen atom. The alkene transforms into an alkane, a saturated hydrocarbon. What was once an open, reactive site now becomes a stable, single-bonded stretch. This process, hydrogenation, is vital. It's how we turn liquid vegetable oils into solid margarines, saturating their fatty acid chains, changing their physical properties from a shimmering liquid to a waxy, greasy substance. It's a profound shift, all thanks to the simple addition of hydrogen across a double bond. The mirror image of addition is the elimination reaction. If addition is about gaining new partners, elimination is about gracefully letting go, creating space, often forming a new double or triple bond in the process. Here, two atoms or groups of atoms are removed from adjacent carbons in a molecule, and in their departure they leave behind a new unsaturation, a new double bond. It's like two dancers stepping out of the circle, and the remaining dancers, to close the gap, link arms more tightly, forming a new, stronger connection. Consider an alcohol with its hydroxyl OH functional group. Under the right conditions, perhaps with the strong acid and gentle heat, the hydroxyl group and a hydrogen atom from an adjacent carbon can be coaxed to depart, forming a molecule of water. What remains is a carbon-carbon double bond, an alkene. The alcohol, once content with its single bonds, has shed some of its molecular weight, revealing a new energetic potential in its unsaturated form. This dehydration is a common path to creating alkenes, those versatile building blocks for countless other organic molecules. Finally, though less common as a primary category for beginners, we encounter rearrangement reactions. These are the internal transformations where the atoms within a single molecule simply change their positions, like dancers shifting places on the floor without anyone leaving or joining the group. The overall chemical formula remains the same, but the connectivity, the very architecture of the molecule, is altered, resulting in a structural isomer. It's a subtle but significant internal resculpting, often driven by the quest for even greater stability or facilitated by specific catalysts. Each of these reaction types, substitution, addition, elimination, rearrangement, represents a fundamental language in the story of organic chemistry. They are the verbs, the actions that drive the plot forward. But just as dancers need music, light, and a stage, molecules need specific condition to perform their transformations. Temperature can be the driving rhythm, providing the energy for bonds to break. Pressure can influence the closeness of the dancers. Solvents are the medium, the atmosphere in which the dance takes place, subtly influencing the interactions. And then there are the catalysts. Catalysts are the unsung heroes, the quiet choreographers of the molecular world. They are substances that speed up a reaction without being consumed in the process. They don't change the ultimate destination of the reaction, but they provide an easier, less energetically demanding pathway, a smoother, more elegant route for the dancers to take. In biological systems, these catalysts are called enzymes, and they're astonishingly precise, guiding specific transformations with breathtaking efficiency and selectivity. Without enzymes, the complex symphony of life, the myriad reactions occurring within every cell, would grind to a halt. As we ponder these transformations, we begin to appreciate the dynamic nature of all matter around us. The food we eat is broken down and rebuilt through a cascade of organic reactions. The medicines we take exert their effects by engaging in specific molecular dances within our bodies. The plastics, the fuels, the dyes, the very fabric of our modern world, all are products of purposeful molecular transformation, guided by the principles of organic reactions. This quiet understanding of how molecules interact, how they break and form bonds, how they rearrange themselves, is profoundly empowering. It allows us not just to observe, but to design, to create, to harness the very language of life for our own purposes. We are not merely spectators. We are becoming fluent in the universe's most beautiful and intricate poem, learning to read its verses, to understand its grammar, and perhaps one day to write our own. The journey continues, dear friends, ever deeper into the heart of matter. We have seen the static structures, we have understood their shapes, and now we begin to grasp their movements, their transformations. But what forces truly guide these electrons? What invisible hands pull and push them from one bond to another? Next, we shall delve into the very nature of these bonds, exploring the subtle differences in their character and how these differences dictate the flow of electrons, the very essence of reactivity. For in the world of organic chemistry, the electrons are the true artists, and their dance is the story of everything. We stand at the precipice of a profound question, do we not? We have watched molecules transform, witnessed atoms reshuffle themselves in elegant ballets of creation and dissolution. But what truly is the unseen hand that guides these transformations? What whisper dictates the path of an electron, urging it from one atom's embrace to another's? It is a question that leads us deeper into the very heart of molecular existence, into the subtle, powerful forces that shape everything we know. Imagine, if you will, that each atom in our grand molecular dance holds a certain magnetic appeal for electrons. Some atoms are more persuasive, more insistent in their pull. This inherent persuasiveness, This quiet, fundamental desire for electrons is what we call electronegativity. It is a measure of an atom's ability to attract the shared electrons in a covalent bond. Think of it as a gentle tug of war, a silent competition for the shimmering clouds of probability that are the electrons. When two atoms of differing electronegativity form a covalent bond, the shared electrons are not truly shared equally. No, the more electronegative atom will pull the electron density a little closer to itself, like a quiet child hoarding a favourite toy. This creates a subtle imbalance, a partial negative charge V on the more electronegative atom, and a partial positive charge D+ on the less electronegative atom. We call such a bond a polar covalent bond, a bond with the tiny inherent asymmetry, a whisper of charge. Consider water H2O. Oxygen is significantly more electronegative than hydrogen. What does this mean for our quiet architects? It means the oxygen atom gently but firmly draws the electron density from both hydrogen atoms toward itself. The oxygen atom becomes slightly negative, the hydrogen atom slightly positive. This isn't a full transfer of electrons, not an ionic bond, but rather a distortion of the electron cloud, a subtle leaning. These partial charges create a dipole, a molecular magnet with a positive end and a negative end. And it is these tiny inherent dipoles, these molecular whispers of charge, that dictate so much of how molecules interact with each other, how they recognize and embrace or repel their neighbors. These polar bonds are the hidden currents within the molecular ocean guiding the flow of electrons. Where there is a partial positive charge, an atom is slightly electron poor, making it an inviting target for electron-rich species. Where there is a partial negative charge, an atom is slightly electron-rich, ready to reach out and share its abundance. This fundamental principle, that electron-rich areas seek electron-poor areas, is the engine of countless chemical reactions. It is the language of attraction, the silent dialogue that orchestrates molecular change. Sometimes, however, the electron density isn't simply pulled along a single bond. Sometimes the electrons are so fluid, so restless that they can be delocalized over several atoms, spreading out their influence like a shimmering wave across a pond. This phenomenon is known as resonance. Imagine a molecule that can be drawn in two or more valid Lewis structures, where only the placement of pi electrons, those in double or triple bonds, and lone pairs differs. These aren't different molecules, they are different representations of a single average structure. The true molecule is a resonance hybrid, a blend of all these contributing structures, where the electrons are not confined to one specific location but are spread out delocalized. Think of it like a blended color. You might describe a certain shade as blue-green, but it's not sometimes blue and sometimes green. It's always blue-green. A single, unique hue. Similarly, a molecule exhibiting resonance doesn't flicker between its resonance forms. It is the hybrid, a more stable, more harmonious arrangement where the electron density is diffused, reducing localizer's charge and thus reducing energy. This delocalization is a profound stabilizing force, making certain molecules remarkably unreactive or influencing where they will react, is the molecular equivalent of sharing the burden, spreading the energy, creating a quiet strength. Beyond the immediate bond, the electronegativity of an atom can also reach out and influence its neighbors through the sigma bonds, albeit to a lesser extent. This is called the inductive effect. An electronegative atom, like a persistent tugger, can pull electron density not just from the atom it's directly bonded to, but also more weakly from the next atom in the chain and the next. It's like a ripple effect, a subtle but pervasive influence that gradually diminishes with distance. This effect can make a carbon atom, even one not directly bonded to the electronegative atom, slightly more electron-poor, subtly altering its reactivity, making it a more inviting target for an electron-rich species. These are the quiet, cascading forces that shape the molecular landscape, guiding the electrons to their next dance partner. Now let us turn our gaze to one of the most fundamental reactions in all of chemistry, a reaction driven entirely by the desire for stability and the movement of electrons: acid-base reactions. At their core, these are elegant exchanges, a seeking of balance. You may have encountered acids and bases before, perhaps in the context of pH, but let us look deeper, through the lens of electron movement. One common way to understand them is through the Bronsted-Lowry definition. An acid is a proton, H please donor, and a base is a proton acceptor. Imagine a molecule with a hydrogen atom that is particularly eager to leave, perhaps because it's bonded to a very electronegative atom, making its bond polar and weakening its hold. This molecule is an acid. When it encounters a base, a molecule with a readily available pair of electrons, a lone pair or a pi bond, that can reach out and embrace that proton, a transfer occurs. The proton leaves the acid, taking no electrons with it, and is taken up by the base. The acid becomes its conjugate base, and the base becomes its conjugate acid. But let us refine this view further to truly appreciate the electron's role. The Lewis definition of acids and bases offers us a more direct glimpse into the electron's journey. A Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. This definition elegantly encapsulates all other acid-base definitions and, crucially, highlights the movement of electron pairs. When a Lewis base with its available electron pair encounters a Lewis acid, which has an empty orbital or a partial positive charge, the electron pair from the base reaches out and forms a new covalent bond with the acid. It is a direct act of sharing, a new embrace forged by electrons seeking stability. The base donates its electron pair, the acid accepts it. This is the very essence of electron flow in action, the quiet, deliberate dance of forming and breaking bonds. Why does an acid donate a proton? Because the resulting conjugate base, after losing the proton, can often better stabilize the negative charge left behind. This stability might come from electronegativity, from resonance, or from the inductive effect, all the principles we just explored. A strong acid forms a stable conjugate base, a testament to the molecule's ability to gracefully accommodate the change in electron density. And why does a base accept a proton? Because it can use its electron density to form a stable new bond, becoming more balanced and content. These concepts, electronegativity, polar bonds, resonance, inductive effects, and acid-base chemistry as the dance of electron pairs, are not isolated facts. No, they are the profound interwoven tapestry that dictates the reactivity of every organic molecule. They are the subtle forces that guide the electrons, the true artists of chemistry, in their endless creation. When we look at a molecule now, we no longer see just a collection of atoms. We see a landscape of electron density, a topography of partial charges, areas of richness and areas of scarcity. We see the potential for resonance, the subtle pull of inductive effects, the eager embrace of an electron pair donor meeting an electron pair acceptor. We begin to understand why certain bonds are broken, why new bonds are formed, why one part of a molecule is attacked while another remains untouched. It is here in this quiet contemplation of electron flow that the true magic of organic chemistry reveals itself. It is the language of life, yes, but it is also the physics of attraction, the poetry of stability, the silent, invisible currents that power every biological process, every flicker of thought, every beat of a heart. From the simplest hydrocarbon to the most complex enzyme, these fundamental principles are at play, orchestrating the dance. So as the quiet evening deepens and perhaps the night sky outside your window invites reflection, let us carry this understanding with us. Let us see not just the stars, but the invisible forces that bind the universe, from the grandest galaxies to the tiniest, most elegant molecular transformations. The journey into organic chemistry is a journey into the heart of creation, guided by the wondrous, ceaseless dance of electrons. And we are only just beginning to truly appreciate its rhythm. This ceaseless dance, this elegant ballet of attraction and repulsion, is the very heart of organic chemistry, a story told not in words, but in the invisible currents of electron flow. And as we continue our journey, we find ourselves drawn ever deeper into the intricate choreography, seeking to understand not just what happens, but why and how these tiny artists orchestrate such profound transformations. Tonight, under the quiet gaze of the stars, we will peer into the very heart of this choreography. We speak of electrons, these restless, shimmering beings, as the true artists, the orchestrators. But how do they move? What is their precise path, their sequence of steps, as a molecule transforms? This is where we encounter the profound beauty of reaction mechanisms. Imagine a grand ballet. We have seen the dancers' atoms and their costumes, functional groups. We have even understood the overarching theme of the performance, the type of reaction. But a mechanism, my friends, is the choreographer's score. It is the step-by-step instruction manual, charting the precise movements of every dancer, every subtle shift of weight, every delicate linkage and release. It is the language that tells us, with breathtaking clarity, how bonds break and new bonds form. To speak this language, we need a special kind of notation, a visual shorthand that maps the unseen. We call them curved arrows. These aren't just arbitrary squiggles. They are elegant sound symbols, laden with meaning. A curved arrow, you see, always begins where electrons are. An electron pair in a bond, or a lone pair on an atom, and points precisely to where those electrons are going, either to form a new bond or to become a lone pair on an atom. It's a whisper, a silent directive, revealing the trajectory of electrical charge. Most commonly, we encounter the double-headed curved arrow, a graceful arc signifying the movement of an entire pair of electrons. It's like two dancers moving in perfect synchronicity, hand in hand, from one position to another. This is the signature of polar reactions, those transformations we discussed earlier, driven by the subtle tugs and pushes of electronegativity, where electron-rich regions seek electron-poor regions. But sometimes the dance is different, more solitary, more abrupt. There are moments when a bond does not break cleanly, with one atom taking both electrons. Instead, the electron pair splits and each atom takes one electron. This is depicted by a single-headed curved arrow, often called a fishhook arrow, a solitary sharp movement indicating the journey of just one electron. This leads us into the realm of radical reactions, where molecules possess an unpaired electron, making them fiercely reactive, seeking a partner with an almost desperate intensity. Think of it as a single dancer momentarily alone searching for a mirror image to complete a pair. Let us focus for a moment on the more common polar reactions, where the dance of electron pairs dictates the flow. When a covalent bond breaks in such a way that one atom retains both of the shared electrons, we call this heterolytic cleavage. It's a rather dramatic separation, leaving one atom with a negative charge, an excess of electrons, and the other with a positive charge, a deficit of electrons. These fleeting charged entities are incredibly important. They are the Planck's intermediates of our molecular ballet, the temporary forms that molecules adopt mid-transformation, often existing for mere microseconds before reacting further. They are like a dancer frozen mid-leap, poised for the next movement but not yet having landed. Consider a carbon atom. With its 4 strong arms, it usually forms 4 bonds, but in the midst of a reaction, if it loses a bond and is left with only 3 bonds and a positive charge, it becomes a carbocation. Imagine our carbon architect suddenly missing a Lego brick, leaving a positive void. This carbocation is electron deficient, a hungry entity yearning for electrons to regain its stability. It acts as an electrophile, an electron lover, actively seeking electron-rich partners known as nucleophiles to complete its octet and neutralize its charge. Conversely, if a carbon atom, through heterolytic cleavage, gains an extra pair of electrons and carries a negative charge, it transforms into a carbanion. Now our carbon architect has an extra unattached Lego brick, making it electron-rich and seeking to donate that pair to form a new bond. It acts as a powerful, yes, nucleophile, a nucleus lover, drawn to positively charged centers. Then there are the radicals born from homolytic cleavage, possessing that lonely unpaired electron. These are the wildcards of organic chemistry, incredibly reactive, driven by an urgent need to find another electron to form a stable pair. They often initiate chain reactions, a cascade of transformations, as they relentlessly seek stability. These intermediates, carbocations, carbanions, radicals, are the ephemeral characters in our story, appearing and disappearing in the blink of an eye. Their existence, however brief, is critical to understanding the pathway a reaction takes. But there is an even more fleeting state, a moment of profound transformation that is utterly impossible to isolate. This is the transition state. Imagine our dancers at the very apex of a leap, or in the precise instant when one hand releases another, just as a new hand grasps. It is the highest energy point along the reaction pathway, where old bonds are simultaneously breaking and new bonds are simultaneously forming. It's a blurred, unstable configuration, existing for an immeasurable fraction of a second, representing the absolute peak of the energy barrier that molecules must surmount to transform. We spoke in an earlier chapter about activation energy, that invisible hill molecules must climb to react. The transition state is the very summit of that hill. It's not an intermediate, which has a distinct, albeit brief, existence. The transition state is the process itself, caught in its most vulnerable and energetic moment. It is the whisper of change, the very breath of transformation. By mapping these steps with curved arrows, by identifying the intermediates that momentarily exist, and by conceptualizing the transition states that mark the energy peaks, we gain an unparalleled understanding of the molecular world. We can predict how molecules will react, design new synthetic pathways, and even understand the exquisite precision of life's own molecular machinery. For example, consider a simple acid-base reaction, which we explored in Chapter 5. A base rich in electrons uses a lone pair to pluck a proton, an H+, from an acid. The curved arrow beautifully illustrates this. It begins at the lone pair on the base and points directly to the hydrogen atom of the acid. Simultaneously, another curved arrow shows the electrons from the bond between that hydrogen and its parent atom shifting back to the parent atom, forming a new lone pair. It's a perfectly choreographed exchange, driven by the ceaseless desire for stability, all laid bare by the elegant simplicity of curved arrows. This deep dive into reaction mechanisms is not merely an academic exercise. It is an invitation to witness the universe's most beautiful and intricate poem, stanza by stanza, word by word. It allows us to appreciate the genius of nature, the silent architecture that underpins all life, all matter, all existence. It is a testament to the quiet brilliance of electrons, these tiny artists who, with every graceful movement, paint the vibrant tapestry of our world. As we conclude this contemplation, I invite you once more to gaze at the night sky outside your window. Each star, each galaxy, is a testament to fundamental forces, to the dance of matter and energy. And within the smallest molecules, within the very fabric of life, the same profound principles are at play, orchestrated by the invisible currents of electron flow. To understand this choreography is to understand the language of creation itself. And as we continue our journey, we will find that these mechanisms are not just isolated events, but are part of a grander, interconnected web, influencing everything from the taste of an apple to the intricate workings of our own bodies. In our quiet exploration, chapter by chapter, we have traced the invisible threads that weave the fabric of organic chemistry. We have peered into the heart of carbon, witnessed the elegant ballet of electrons, and learned the precise language of curved arrows which articulate every step of a molecular transformation. We've seen how these arrows map the journey of electrons, from a starting material through fleeting intermediates to a final stable product. But now, as the gentle quiet of the evening deepens, a new question arises, one that connects these individual dances into a grander performance. How do these singular steps, these isolated mechanisms, connect within a larger, more intricate web? How do we move beyond a single transformation to build the truly complex molecules that populate our world? From the simplest sugars that sweeten our lives to the intricate proteins that animate them. Think of it not as a single word, but as a profound story. Each reaction mechanism we've discussed is like a beautifully crafted sentence, perfectly structured, conveying a specific idea, but a story, a truly resonant narrative, is built from many sentences, strung together with purpose and grace. Organic synthesis, the art and science of building organic molecules, is precisely this. The thoughtful, deliberate stringing together of many distinct reaction steps, each with its own mechanism, its own precise choreography, to construct a molecule of exquisite complexity and function. Few of the molecules we encounter in life, or indeed few of the molecules we endeavour to create in the laboratory, spring forth fully formed from a single reaction. No, they are often the culmination of a patient multi-step journey, a carefully planned sequence of transformations. Imagine a master artisan weaving a magnificent tapestry. They do not simply throw threads at a loom. They select each colour, each material, and meticulously interlace them, strand by strand following a grand design. Each interweaving is a small, precise action, but it contributes to the breathtaking beauty of the whole. This is the essence of a multi-step synthesis. We begin with simpler, more readily available molecular starting materials, our basic threads. Then, through a series of carefully chosen reactions, we modify them, adding new functional groups, extending carbon chains, forming rings, or introducing specific three-dimensional arrangements. Each step is a purposeful modification, preparing the molecule for the next. Like a dancer moving from one pose to another, each transition setting the stage for the next elegant movement. Consider for a moment a simple hydrocarbon, a long, quiet chain of carbon atoms. It is stable, unreactive, content in its simplicity. But what if we wish to transform it into something more dynamic, more interactive? Perhaps an alcohol with its polar hydroxyl group capable of forming hydrogen bonds and acting as a solvent, or a carboxylic acid with its acidic proton ready to engage in acid-base chemistry. We cannot simply will it into being. Instead, we embark on a journey. We might first introduce a halogen, perhaps chlorine, through a radical substitution mechanism we've briefly touched upon, replacing a hydrogen atom with a chlorine atom. This creates a new, more reactive intermediate molecule. This chlorinated molecule, though still simple, now possesses a new personality, a new point of vulnerability. The carbon atom bonded to the chlorine is now slightly positive, a target for electron-rich species. From this intermediate we can then perform another reaction. We might expose it to a strong base which, through a substitution mechanism, could replace the chlorine with a hydroxyl group, thus creating our desired alcohol. Or, perhaps, we could use a different set of reagents, and through an elimination reaction, create a double bond, opening up an entirely new pathway for further transformations. Each of these steps, each of these sentences in our molecular story, has its own precise mechanism, its own set of curved arrows detailing the electron flow. But the true art lies in seeing how these sentences connect, how one reaction's product becomes the next reaction's reactant. It is a logical progression, a molecular conversation where each statement builds upon the last. This deliberate design of a synthetic pathway often involves a fascinating mental exercise known as retrosynthesis. Instead of thinking forward from starting materials to a final product, a chemist often thinks backward. They look at the target molecule, the desired masterpiece, and ask, what was the immediate precursor to this molecule? What was the last reaction that formed it? And then, what was the precursor to that molecule? And so on, step by step, unwinding the synthesis like a spool of thread until they arrive at simple, readily available starting materials. It is like an architect dreaming of a magnificent structure and then working backward to envision the foundations, the beams, the walls, until they reach the raw materials. This backward thinking is a powerful tool, allowing us to envision the entire web before we even begin the first dance. Yet even with a clear pathway in mind, some molecular dances are slow, hesitant, or require a tremendous burst of energy to begin. This is where the truly wondrous role of a catalysis enters our story. Catalysts are the invisible guides, the silent facilitators, who make these dances possible or profoundly more efficient without ever joining the dance themselves. They are the wise mentors who show the molecules a new, easier path, a lower energy route to transformation. A catalyst does not change the ultimate destination of a reaction, it simply changes the journey. It provides an alternative mechanism, one with the significant lowest activation energy that energetic hurdle molecules must overcome to react. Imagine a mountain pass. The catalyst doesn't move the mountain, but it might reveal a gentle, winding path around it, rather than forcing climbers to scale its steepest face. Molecules, in the presence of a catalyst, can traverse this easier path, transforming much more readily and quickly. We often encounter catalysts as acids or bases, gently assisting in the transfer of protons, or as sophisticated metal complexes, providing temporary docking sites for molecules to interact and rearrange. They are not consumed in the reaction. They emerge unchanged, ready to guide countless other molecules along the same path. This ability to facilitate transformation without being used up makes catalysts incredibly powerful, allowing us to synthesize complex molecules with greater efficiency, less waste, and often under milder, more sustainable conditions. They are the unsung heroes of countless industrial processes and, profoundly, of life itself. Indeed, if we speak of catalysts, we must speak of enzymes. These are nature's master choreographers, the ultimate molecular architects of life. Enzymes are biological catalysts, almost always proteins, crafted with exquisite precision to facilitate the vast array of chemical reactions that sustain every living cell. From the digestion of our food to the replication of our DNA, enzymes are at the heart of every biochemical pathway, every intricate step in the story of life. What makes enzymes so extraordinary is their unparalleled specificity. Each enzyme is typically designed to interact with one, or a very small number, of specific molecules called substrates, guiding them through a particular reaction with astonishing speed and efficiency. They are like master key makers, with each key, enzyme, perfectly fashioned to open one specific lock substrate and initiate a precise transformation. This specificity is crucial. It ensures that the right reactions happen at the right time, preventing molecular chaos and orchestrating the harmonious symphony of life. So the web of organic chemistry is not just about individual mechanisms, but about how these mechanisms are linked in purposeful sequences, often guided and accelerated by catalysts. But within this web, there is another layer of profound beauty and challenge. Selectivity. Imagine a molecule that has several potential sites where a reaction could occur, several paths it could choose to dance down. How do we ensure it takes the desired path, forming the desired product, rather than a mixture of possibilities or worse, an unwanted side product? This is the challenge of selectivity, and it is a testament to the ingenuity of organic chemists. We learn to control the dance by carefully choosing our reaction conditions. The solvent, the liquid environment in which the reaction takes place, can play a crucial role, influencing how molecules interact and which pathways are favored. Imagine a dance floor. A slick, polished floor might encourage graceful glides, while a rough, textured one might favor sharp, quick turns. Similarly, the molecular texture of the solvent can subtly steer the reaction. Temperature is another key dial. Increasing temperature often provides more energy, allowing molecules to overcome higher activation barriers, but it can also lead to less selective reactions, as molecules gain enough energy to explore multiple pathways. Lower temperatures, conversely, can sometimes favor a specific lower energy pathway, leading to greater selectivity. And of course, the choice of reagent itself is paramount. Just as a chef selects specific ingredients for a dish, a chemist chooses a reagent specifically designed to react at a particular site on a molecule, or to favor a specific type of transformation. Some reagents are gentle and discerning, reacting only with specific functional groups. Others are more aggressive, reacting broadly. Understanding these nuances allows us to guide the molecular dance with precision. Ultimately, the journey through organic chemistry reveals a profound interconnectedness. Each atom, each bond, each electron movement, each reaction mechanism, each synthetic step, each catalyst, and each carefully chosen condition, they are all threads in an immense shimmering tapestry. This tapestry is the story of how matter transforms, how life builds itself, and how we, as curious observers and aspiring architects, can learn to understand and even participate in this grand molecular creation. As we gaze upon the quiet vastness of the night sky, we are reminded that the same fundamental principles that govern the dance of stars in galaxies also govern the unseen dance of electrons in molecules. Organic chemistry, then, is not merely a collection of facts. It is a profound poem of existence, a silent architecture that underpins everything we see, touch, and are. The wonder, as always, is in the details, in the quiet revelation of how these intricate pieces fit together to form the beautiful, dynamic, living world. And our adventure, our slow and thoughtful exploration of this wonder, continues. We have journeyed far, haven't we? From the quiet brilliance of a single carbon atom, through the delicate dance of electrons, the intricate choreography of reaction mechanisms, and the grand design of multi-step syntheses, we have learned to read the whispers of atoms, to understand their desires for stability, and to even orchestrate their transformations. But what, my friends, is the ultimate result of all this profound understanding? What masterpiece do these quiet architects build with the language we are slowly mastering? The answer lies in the almost infinite tapestry of organic compounds themselves. Each principle we have explored, from the magic of functional groups to the destiny woven into molecular shape, from the invisible currents of electron flow to the deliberate steps of synthesis, culminates in the existence of these molecules. They are the tangible expressions of organic chemistry, the very building blocks of life, the pigments of our world, the flavors on our tongue, the medicines that heal, and the materials that shelter us. Imagine, if you will, that we have been studying the grammar and syntax of a universal language. Now, in this quiet moment, we begin to explore the vast literature written in that language. Each class of organic compounds is like a distinct genre, with its own recurring motifs, its own characteristic melodies, and its own unique story to tell. And just as the skilled linguist can discern the essence of a text from its structure, so too can we, by understanding the molecular architecture, predict and appreciate the properties of these countless compounds. At the heart of this classification, as we touched upon in our early explorations, lies the functional group. These specific groupings of atoms clinging to the carbon skeleton like precious jewels are the true markers of a molecule's identity. They are the conductors of the molecular symphony, dictating not just the note, but the entire feel and rhythm of the piece. They are the vibrant brushstrokes that give each compound its unique colour and texture in the grand painting of existence. Let us begin our gentle stroll through this molecular gallery, observing some of the most prominent classes. We first encountered the simplest of these, the hydrocarbons, molecules composed solely of carbon and hydrogen. They are the foundational scaffolding, the quiet, sturdy bones upon which all other structures are built. We spoke of alkanes, those saturated single-bonded chains, often waxy and inert, forming the backbone of fuels and lubricants. Think of them as the steady, unchanging bass notes in our symphony. Then came the alkenes, with their double bonds, introducing points of reactivity, eager to participate in addition reactions, like a sudden energetic rhythm. And the alkynes, with their triple bonds even more tightly coiled, holding a potent energy, a sharp, piercing sound. And finally the elegant cyclic dance of the aromatic compounds, like benzene, with their delocalized electrons humming in a stable resonant harmony, giving rise to the scents and flavors we often associate with organic itself. These hydrocarbons, though seemingly simple, are the bedrock, the fundamental canvas. But the true diversity blossoms when other elements, particularly oxygen and nitrogen, enter the scene, bringing their own unique electronegativity and bonding preferences, transforming the character of the entire molecule. Consider first the family of compounds graced by the presence of oxygen. The alcohols are perhaps the most familiar to us, characterized by the hydroxyl group, an oxygen atom bonded to a hydrogen atom, OH, attached to a carbon chain. Imagine this. OH group as a tiny magnetic hand reaching out. Because of oxygen's greater electronegativity, it pulls electrons away from both carbon and hydrogen, creating polarity within the bond. This polarity, especially the bond between oxygen and hydrogen, allows alcohols to engage in a special kind of intermolecular embrace known as hydrogen bonding. It's like molecules holding hands, forming transient but strong connections. This gentle holding makes alcohols more sociable than their hydrocarbon cousins. They have higher boiling points because it takes more energy to break these molecular handshakes, and many, like ethanol, mix readily with water, the ultimate polar solvent, because they can form new hydrogen bonds with water molecules. They are the gentle, flowing melodies, often found in solvents, fuels, and of course beverages. Next, we encounter the ethers, where an oxygen atom acts as a bridge, connecting two carbon groups, ROR. Unlike alcohols, the oxygen in an ether doesn't have a hydrogen atom directly attached to it, so it cannot participate in hydrogen bonding with itself. This makes ethers less polar and less reactive than alcohols, often serving as excellent, mild solvents in the laboratory, dissolving many organic compounds without interfering in their reactions. They are the quiet, stable background harmonies, allowing other instruments to shine. Then comes the striking presence of the carbonyl group, a carbon atom double bonded to an oxygen atom, CO. This seemingly simple arrangement is a powerhouse of reactivity, a vibrant, percussive element in our molecular symphony. When this carbonyl group is at the end of a carbon chain, bonded to at least one hydrogen atom, we have an aldehyde. Think of the sharp, pungent scent of formaldehyde, or the sweet, almond-like aroma of benzaldehyde. Aldehydes are eager participants in reactions, often acting as building blocks for more complex molecules. When the carbonyl group is nestled within a carbon chain bonded to two other carbon atoms, we have a ketone. Acetone, the common nail polish remover, is a perfect example. Ketones are generally less reactive than aldehydes, but still possess that inherent polarity and the potential for a wide array of transformations. Both aldehydes and ketones are central to metabolism and the synthesis of countless organic compounds, their reactivity stemming from the electron-withdrawing nature of the oxygen, making the carbonyl carbon slightly electron deficient and ready to accept electron pairs. They are the rhythmic driving force giving structure and urgency to the molecular dance. Moving further along the oxygen-containing compounds, we arrive at the carboxylic acids. Here, the carbonyl group is directly attached to a hydroxyl group, COH. This combination is particularly fascinating. The presence of the electronegative oxygen atom stabilizes the negative charge that forms when the hydrogen of the hydroxyl group is released as a proton. This makes carboxylic acids acidic. They readily donate a proton. Think of the tartness of vinegar, or acetic acid, or the sting of an ant bite, formic acid. They also engage in incredibly strong hydrogen bonding, forming stable dimers, two molecules linked together, and having surprisingly high boiling points. Carboxylic acids are the fundamental building blocks of fats, proteins, and many biological pathways. They are the profound resonating chords, providing depth and structure. Closely related to carboxylic acids are the esters. These are formed when a carboxylic acid reacts with an alcohol, replacing the acidic hydrogen with an alkyl group, RCOR. Esters are often celebrated for their delightful aromas, the sweet scent of ripe fruit, the fragrance of flowers. Banana oil, isoamyl acetate, pineapple flavour, ethyl butyrate, and apple scent, methyl butyrate, are all esters. They are generally less polar than carboxylic acids and do not hydrogen bond with themselves, contributing to their volatility and ability to waft through the air. They are the light, airy arpeggios, adding sweetness and charm to the molecular symphony. Now, let us turn our attention to the compounds that embrace nitrogen, another vital element in the language of life. The amines are organic compounds containing a nitrogen atom with a lone pair of electrons, often bonded to one or more carbon atoms, RNH2, R2NH, R3N. That lone pair of electrons makes amines basic. They are eager to accept a proton, much like a generous host offering shelter. This basicity is crucial in biological systems, as many neurotransmitters, hormones and drugs are amines. Think of the pungent smell of fish due to trimethylamine, or the complex structures of alkaloids like caffeine and nicotine. Amines can also participate in hydrogen bonding, though generally weaker than alcohols, influencing their physical properties. They are the vibrant, sometimes pungent brass section, adding a distinctive character and reactivity. Finally, we encounter the amides. These compounds feature a carbonyl group directly bonded to a nitrogen atom, RCONR2. Unlike amines, the nitrogen in an amide is much less basic. The electron withdrawing effect of the carbonyl oxygen delocalizes the lone pair on the nitrogen, making it less available to accept a proton. Amides are incredibly stable, and their strong hydrogen bonding capabilities are paramount. The most famous amides are the peptide bonds that link amino acids together to form proteins, the very machinery of life. Here, the amide bond is not just a functional group, it is the fundamental stitch that weaves together the grand, intricate fabric of biological existence. They are the strong, enduring backbone, the very rhythm section that holds the entire biological orchestra together. As we reflect on these diverse families of compounds, a deeper truth emerges. Their more macroscopic properties, how they behave in the world, their melting points, their boiling points, their solubility, their smells, their tastes, are all direct consequences of their molecular structure. The presence or absence of a hydroxyl group dictates whether a molecule can form hydrogen bonds, profoundly affecting its boiling point and its ability to dissolve in water. The carbonyl group's polarity makes a molecule more reactive, while the delocalization of electrons in an aromatic ring grants it exceptional stability. It is a beautiful, intricate dance between the atomic and the observable. When we smell the sweet fragrance of an ester, we are experiencing the volatility of a molecule with weaker intermolecular forces, allowing it to easily waft into our olfactory receptors. When we feel the waxy texture of a long-chain alkane, we are encountering the cumulative effect of many weak London dispersion forces, holding the non-polar molecules together. When a drug, often an amine or an alcohol, interacts specifically with a receptor in our body, it is a testament to the precise molecular fit, the exquisite complementarity of shapes and electron distributions. This ability to classify, to understand the personality of molecules based on their functional groups, is not merely an academic exercise. It is a powerful lens through which we can perceive the underlying order and elegance of the natural world. It allows chemists to predict, to design, and to create molecules with specific desired properties, whether for new medicines, advanced materials, or sustainable energy solutions. So as we close this chapter, let us hold on to this profound realization. Organic chemistry is not just about isolated atoms or abstract reactions. It is about the vast living landscape of molecules they create. It is about the symphony of structures, each playing its unique part, contributing to the grand, intricate poem of existence. We are learning not just the vocabulary, but the very nuances of expression in the language that describes all life, all matter, all wonder. And with each new family of compounds we encounter, the story becomes richer, the understanding deeper, and the connection to the universe outside your window more profound. What incredible harmonies will we discover next as we continue to listen to the silent music of the molecular world? Welcome, quiet explorers, to another contemplative evening within our dreamy academy. As the soft light of the stars begins to pepper the vast canvas outside your window, we turn our gaze inward toward the very stars of the molecular universe, the compounds that sing the song of life itself. In our previous journeys, we have meticulously built a foundation. We've admired carbon's unparalleled versatility, observed the distinct personalities lent by functional groups, recognized the profound significance of molecular shape, and understood the dynamic ballet of chemical reactions, all orchestrated by the tireless electrons. We've even begun to classify the vast tapestry of organic compounds, seeing how their intricate structures dictate their macroscopic properties, from the slick feel of an oil to the crisp aroma of an aldehyde. But what if I told you that all these principles, all these elegant dances of atoms and electrons, culminate in something truly extraordinary? What if I told you that the quiet architecture we've been exploring is the very blueprint for existence, for the rustle of leaves, the warmth of a heartbeat, the flash of a thought? Tonight, we step into the grand gallery of biomolecules, the magnificent structures that organic chemistry builds to sustain life. These are not just any compounds, they are the ultimate expressions of chemical elegance, the masterpieces crafted by the universe's most patient architect. Think of them as the fundamental components of a living symphony, each playing a crucial role, yet all harmonizing through the very principles we've diligently uncovered. We begin our exploration with the carbohydrates, often known simply as sugars. The very word sugar might evoke images of sweetness, of a quick burst of energy, and indeed, these molecules are nature's primary fuel, but they are much more. At their heart, carbohydrates are polyhydroxyaldehydes or ketones, meaning they are organic molecules adorned with multiple hydroxyl OH groups and either an aldehyde or a ketone functional group. Their general formula often reflects a ratio of carbon, hydrogen, and oxygen of approximately 1:1, like a hydrated carbon, hence the name. Imagine a tiny molecular tree, its branches laden with hydroxyl groups eager to interact with water. This abundance of hydroxyls makes most carbohydrates wonderfully soluble in water, a crucial property for their transport within living systems. The simplest carbohydrates are the monosaccharides, the single-unit sugars. Glucose, for instance, a 6-carbon sugar, is the universal energy currency for most living cells. Look closely at its structure, and you'll see the familiar carbon backbone, the aldehyde group at one end, and a cascade of hydroxyls. Remember our discussions on isomerism. Glucose has several stereoisomers, and even the subtle difference between glucose and galactose, a simple flip of a hydroxyl group on just one carbon, is enough to give them distinct biological roles. Our bodies recognize glucose with exquisite specificity, a testament to the power of molecular shape. When two monosaccharides link together through a glycosidic bond, a type of ether linkage formed by a condensation reaction, they form a disaccharide. Lactose, the sugar in milk, is a disaccharide of glucose and galactose. Sucrose, common table sugar, is glucose and fructose. Each linkage, each specific orientation unlocks a new function. But the true grandeur of carbohydrates emerges with the polysaccharides. Vast polymeric chains composed of hundreds or even thousands of monosaccharide units. Here, carbohydrates cease to be mere fuel and become architectural wonders. Starch, for example, is how plants store energy, a coiled, branching chain of glucose units, easily broken down when energy is needed. Cellulose, on the other hand, is the primary structural component of plant cell walls. It too is made of glucose units, but the glycosidic linkages are different, arranged in a way that allows the chains to lie parallel and form strong, rigid fibers. We humans cannot digest cellulose, but it provides the essential fiber in our diets. Think of the difference between a loosely piled stack of Lego bricks, starch easily dismantled, and a meticulously constructed Lego wall, cellulose strong and stable. Carbohydrates are the sweet symphony of life, providing both immediate energy and enduring structure. They are the initial spark and the sturdy frame, all built from the humble carbon atom, adorned with oxygen and hydrogen, following the rules we've learned. Next, we turn our attention to the lipids, a family of molecules often characterized by what they don't do. They don't mix well with water. These are the water-fearing or hydrophobic molecules. The fats, oils, waxes, and steroids that give life its boundaries and its stored reserves. While carbohydrates are defined by their sugar units, lipids are defined by their insolubility in water, a property stemming from their predominantly nonpolar hydrocarbon chains. Picture a long, snaking chain of carbon atoms, each saturated with hydrogen, like a dense thicket of tiny nonpolar bonds. These hydrocarbon tails are the heart of lipid hydrophobicity. They prefer to associate with each other, shunning the polar embrace of water molecules. This fundamental characteristic allows lipids to form critical structures. Consider the key triglycerides, commonly known as fats and oils. These are formed from a single glycerol molecule, a 3-carbon alcohol, attached to 3 long-chain fatty acids via ester linkages. These are the molecules our bodies use for long-term energy storage, offering a more compact and energy-dense form of fuel than carbohydrates. They also provide insulation and protect our organs. The difference between a fat, solid at room temperature, and an oil, liquid at room temperature, often comes down to the saturation of their fatty acid tails. Saturated fatty acids have no double bonds, allowing them to pack tightly, while unsaturated fatty acids, with their characteristic cis double bonds, introduce kinks that prevent tight packing, leading to a liquid state. Remember our discussion on molecular geometry and how it influences macroscopic properties? Here it is, beautifully illustrated in the kitchen. Then there are the phospholipids. Quiet architects of cellular boundaries. These molecules are truly fascinating, possessing both a hydrophilic, water-loving head, containing a phosphate group, and 2 hydrophobic tails, fatty acid chains. This dual nature, this amphipathic quality, is what allows them to spontaneously form the lipid bilayer that constitutes all cell membranes. Imagine billions of tiny molecular gatekeepers arranging themselves into a delicate, dynamic wall, with their water-loving heads facing outward towards the aqueous environment and their water-fearing tails tucked safely inward, away from the water. This bilayer is not just a barrier, it's a selective gateway, controlling what enters and leaves the cell, a testament to the elegant self-assembly driven by simple intermolecular forces. And finally, within the lipid family, we find the steroids, a distinctive class characterized by their 4-ring carbon skeleton. Cholesterol, a well-known steroid, is a crucial component of animal cell membranes, providing fluidity and stability. It also serves as a precursor for other vital steroid hormones such as estrogen and testosterone, which act as powerful signaling molecules orchestrating complex biological processes. The subtle differences in the functional groups attached to this 4-ring core lead to vastly different biological effects, again emphasizing the profound impact of molecular detail. From energy storage to cellular architecture, lipids are the waxy, greasy, yet utterly essential components that define the boundaries and reserves of life. Our journey through biomolecules now brings us to the proteins, arguably the most diverse and functionally crucial molecules of life. If carbohydrates are the fuel and lipids the walls, then proteins are the molecular machines, the workers, the sculptors, and the defenders. They are polymers, long chains built from smaller individual units called amino acids. There are 20 common amino acids, and each one shares a fundamental structure. A central carbon atom, the alpha carbon, bonded to an amino group NH2, a carboxyl group COOH, a hydrogen atom, and a unique side chain, or R group. It is this R group that gives each amino acid its distinct chemical personality. Some R groups are non-polar and hydrophobic, others are polar and hydrophilic, and still others are charged, acidic or basic. When amino acids link together, they do so through a special covalent bond called a peptide bond. This bond forms between the carboxyl group of one amino acid and the amino group of another, releasing a molecule of water in a condensation reaction. Imagine a long string of beads, each bead an amino acid, strung together by these peptide bonds, forming a polypeptide chain. This sequence of amino acids is called the primary structure of a protein, and it is dictated by the genetic code. But a protein is far more than just a linear sequence. This chain spontaneously folds into intricate 3-dimensional shapes, and it is this precise 3D architecture that determines its function. The polypeptide chain first folds into regular patterns, known as secondary structures, primarily alpha helices like a coiled spring, and beta sheets like a pleated ribbon, stabilized by hydrogen bonds between the backbone atoms. These secondary structures then further fold and contort, driven by interactions between the R groups to form the unique tertiary structure of the protein. Hydrophobic R groups might cluster in the interior away from water, while hydrophilic R groups face outward. Disulfide bridges, covalent bonds between sulfur atoms in certain R groups, can act as molecular staples, locking parts of the structure in place. Ionic bonds and van der Waals forces also play their part. This tertiary structure is the protein's functional form, its molecular sculpture. Some proteins, even more complex, consist of multiple polypeptide chains, subunits, that come together to form a quaternary structure. Hemoglobin, the protein that carries oxygen in our blood, is a perfect example, composed of 4 separate polypeptide chains. The functions of proteins are staggering in their diversity. Enzymes. These are biological catalysts, accelerating biochemical reactions by millions or even billions of times without being consumed themselves. Remember our discussion on catalysts in Chapter 7. Enzymes are nature's most exquisite catalysts, highly specific for their substrates, acting as molecular matchmakers. Structural proteins. Collagen provides strength to our skin and bones. Keratin forms hair and nails. Transport proteins. Hemoglobin carries oxygen. Membrane proteins transport molecules across cell membranes, signaling proteins. Hormones like insulin are proteins that carry messages throughout the body. Defense proteins. Antibodies, crucial components of our immune system, recognize and neutralize foreign invaders. Proteins are the ultimate molecular dancers, performing an endless array of movements, each precisely choreographed by its unique three-dimensional form. They are the workhorses and the artists of the living world, all crafted from the simple yet infinitely versatile amino acids. Finally, we arrive at the nucleic acids, the molecules that hold the very blueprint of life, the grand library of genetic information. These are DNA, deoxyribonucleic acid, and RNA, ribonucleic acid, and they are polymers built from repeating units called nucleotides. Each nucleotide is itself a composite molecule, consisting of three parts: a 5-carbon sugar, deoxyribose in DNA, ribose in RNA, a phosphate group, and a nitrogen-containing base. There are 5 main nitrogenous bases: adenine, A, guanine, G, cytosine C, thymine, T found only in DNA, and uracil U found only in RNA. Nucleotides link together through phosphodiester bonds, forming a long sugar phosphate backbone with the nitrogenous bases projecting outward. This forms a single strand of nucleic acid. DNA, the celebrated double helix, consists of 2 such strands coiled around each other, like a spiraling staircase. The magic of DNA lies in the specific pairing of its bases. Adenine always pairs with thymine, AT, and guanine always pairs with cytosine, GC, held together by hydrogen bonds. This complementary base pairing is the key to DNA's ability to store and replicate genetic information with astonishing fidelity. It is the ultimate information storage device, the instruction manual for building and operating an entire organism. RNA, while structurally similar to DNA, typically exists as a single strand and has diverse roles. Messenger RNA, mRNA, carries genetic instructions from DNA to the protein-making machinery of the cell. Ribosomal RNA, RNA, forms part of the ribosomes, the cellular factories where proteins are synthesized. Transfer RNA, tRNA, carries specific amino acids to the ribosome during protein synthesis. RNA is the dynamic worker, translating the blueprint of DNA into the vibrant reality of proteins. Nucleic acids are the silent narrators of evolution, the guardians of heredity, and the architects of individuality. They store the story and they facilitate its telling, all through the elegant arrangement of simple nucleotides, guided by hydrogen bonds and the precise geometry of their components. As we bring this chapter to a close, take a moment to reflect on the incredible journey we've undertaken. From the unassuming carbon atom to the majestic double helix of DNA, every principle we've explored, the quiet stability of bonds, the distinct personalities of functional groups, the profound impact of shape, the dynamic dance of electrons in reactions, finds its ultimate expression in these molecules of life. Biomolecules are not separate from organic chemistry, they are organic chemistry, working in concert, building the intricate machinery that allows us to breathe, to think, to wonder. They are the universe's most beautiful and intricate poem, written in the language of atoms, whispered in the silent architecture of life. In the quiet glow of this evening, I invite you to feel the wonder of it all, the very essence of your being. The cells that make up your body are a testament to the elegant harmony of these molecular structures. We are, quite literally, walking, talking examples of organic chemistry in action. Next time we will continue to explore the deeper harmonies, perhaps delving into the fascinating world of reaction pathways within living systems, or the intricate ways these molecules communicate. For now, let this sense of awe settle upon you as you contemplate the molecular marvels that underpin all existence. Good night, quiet explorers. The journey continues.